Hola.
Hola, Carlos.
Buenas tardes.
Buenas tardes.
Hola.
Hello.
¿Hay algunas preguntas? ¿No? ¿Todo bien? Okay. So, we were talking, what the hell were we talking about? Line emission, right? So we had gone through lots of sort of early quantum mechanics, talked about sort of how we relate absorption and emission via Einstein relations. And so today I wanted to go through a little bit more, some of the basic rules and kind of how we look at the Einstein coefficients and how that kind of leads to some of the labeling of different line species. And then talking about some of the line profiles and that sort of thing, where they come about. Okay, so let's share screen. No. Okay, so we described the sort of fundamental nomenclature of how you describe different lines, and so unfortunately or fortunately for quantum mechanics, if we follow this, the rules or the sort of I guess the different couplings, the different sort of rules and everything, we have certain lines that or certain transitions that are formally allowed within quantum mechanics, and then we have some which seem to be not allowed. And so we can talk about all of the lines which are allowed if we just do a very simple dipole approximation. And so typically those can be summarized in this set of rules here, which are that allowed lines are ones where you don't have a spin flip. So you retain the spin from one level or one place to another. You typically have a change in the orbital angular momentum that is either 0 or plus or minus 1. So it's basically adjacent angular momentums. You have, so this is the total angular momentum, and then you have the individual angular momentum should be plus or minus 1. Then you have the total angular momentum, which also should be either 0 or plus or minus 1 to mirror this, right? This is the sum of this, more or less, and this. And so these two suggest this. However, here you can't go from 0 to 0. And so that's not allowed. And then finally, you have the magnetic orbital or magnetic momentum, and this can either be 0 or plus or minus 1. And again, no 0 to 0. if this thing is zero. So anything that sort of follows these is fine. And so typically an electron going, say, from the ground state to some upper level allowed state, these are known as resonance lines. And they typically will have spontaneous emission coefficients, which are really high. So the order of 10 to the 8 to 10 to the 13 per second. And so a large number of these end up occurring in the ultraviolet. And so one very obvious example of this is the Lambda series of hydrogen, which is going from, as I mentioned in the last class, going from 1 to 2, 1 to 3, 1 to 4, 1 to 5, etc. Right? And so H alpha is at 1216 angstrom, for instance. And so you can think about the expectation value of what's the likelihood of going from one level to the next. And so you can calculate expectation values based on the radial portion of a Hamiltonian, which take the form of an expectation value. So it's the average of the radius in some degree. So 1 over r, 1 over r squared, 1 over r cubed, etc. And so by Kramer's relation here, we would say that this should go as the expectation value should go as 1 over n cubed. And so that suggests that the ground state has a much higher expectation value than the n equals 4 or n equals 5 state, because you should end up populating that much less typically. And so these resonance lines, they're all over the place, and you plug in these sort of spontaneous emission coefficients into our Einstein relations, and we can calculate sort of how the absorption and emission properties will go. So these are for allowed lines, and then there's another subset of lines where these dipole approximation selection rules are sort of not obeyed. And these are typically called forbidden lines. And there's actually a couple different forms of them, semi-forbidden and fully forbidden lines. And so these are generally observed in emission, not so much in absorption. And typically you observe it in emission after collisional excitation. So you need some other process to fill the upper levels, and then you'll see the forbidden lines from those processes. So the forbidden lines, typically one possible way of doing this is via a magnetic dipole transition. And so you have a spin flip, and so delta S equals 1, right? So this is a clear case where here we said no spin flip for the allowed lines, right? So if you have a spin flip, and there are cases where you do, then you will have an emission line. In this case, typically what you will adopt is you will do the magnetic dipole moment. And so the magnetic dipole moment will take the form, looks like this. And so again, it has some frequency of the transition, some time scale for it, and some coefficient. And so very similar to how we had calculated the electric dipole and how we had looked at the spontaneous emission coefficient for the electric dipole, we can do the same thing for the magnetic dipole, and we just plug in essentially the magnetic dipole in its place. So this is the magnetic dipole matrix element. And typically this thing is of the same order as the Bohr magneton. And so we can get an order of magnitude estimate here. So this, if we adopt a frequency in the optical range, so 3 times 10 to the 15 or so, or I guess this is a little bit into UV. And then we have the square of our dipole moment. And so this is equivalent to our Bohr magneton. And this is equivalent to this set of coefficients. So our charge, our Planck constant, our mass of electron, our speed of light, 4 pi. So this thing is about 10 to the minus 40 or so in terms of erg squared per Gauss squared. And so then you would plug this in with this coefficient, and typically you end up with spontaneous emission coefficients, which are of the order of 10 to the 4 or so. So they're significantly less than 10 to the 8, 10 to the 13 for allowed lines. So this is, the occurrence of them is generally slower. And so this is why you need to sort of wait a long time. If you just let a system go naturally, they would tend to go through the allowed transitions. So this particular magnetic dipole line is, if this thing is much larger than this value, typically the lines are called semi-forbidden. So anywhere to where between 10 to the 4 and 10 to the 8, for instance, these would be semi-forbidden. It's a relatively common transition. And so a good example of this is the C3 line at 1909 in the UV. And so it's denoted here, the semi-forbidden is denoted by this bracket here. It only has one bracket. And then if you have two brackets, it's fully forbidden. Another form of the forbidden transition is if you have an instance where the electric quadrupole becomes important, and you have this electric quadrupole transition. And so here then delta L can take the form of plus or minus 2. It actually can be 0 plus or minus 1 or plus or minus 2. And delta J can then be 0 plus or minus 1 or plus or minus 2. But still, you exclude the 0 to 0 possibility. And so here you would have the radiated power goes for a quadrupole would go as the frequency to the 6th power now. And then you have this thing here, which is the quadrupole moment, which we can denote by this, again, a quadrupole matrix element. And so in this case, for instance, you might have the hydrogen atom, and in the hydrogen atom, if we adopt a frequency of 10 to the 15 or so, then the quadrupole moment for hydrogen would be of the order of this. So it would be the order of about 2 times 10 to the minus 52 in these units. And so this would suggest a spontaneous emission coefficient that's of the order of 10 seconds or so. And so in general, in hydrogen, for instance, the dipole moments dominate, but there are some places, some atoms where the quadrupole moment actually can be an important form of sort of energy loss, typically for collisionally ionized gases. So a good example of this is oxygen 3 at 5,700. And then there's another oxygen 3 at 4959 angstroms. That's known as the oxygen sort of double. And so this is a forbidden transition. So you see it's got both brackets there. And so typically whether something is allowed, semi-forbidden, or forbidden depends partially on the terms that are involved and partially on the value of the spontaneous emission coefficient. So in addition to this, you can also have what we call fine structure lines, which are forbidden lines that are within the ground state multiplet. And so typically, so this is the same ground state multiplet, but you go from the 2p32 to the 2p1/2. And this, for instance, is a good example of this is carbon 2 and at 158 angstroms. Or sorry, 158 micron. And so this is actually in the infrared. This is a super strong cooling line in the infrared. And typically, something like 1 or a few % of the total energy that's radiated by gas and dust, it comes out in this line. Then you have the hyperfine structure constants, or hyperfine structure lines. And these are typically lines where the nucleus will exert some influence on the transition. And the best example of this is the spin flip in the hydrogen atom. And so you have the proton, you have your electron, and you could have the spins aligned and then misaligned. And so that spin flip leads to, it's a really relatively low energy transition. So it happens at 21 centimeters in the radio. And then finally, you have something called satellite lines. And these are lines that are produced by excited atom or excited ions. So you have an atom where you've excited something. And so you have an inner shell, which is missing an electron. And so you can have transitions from an upper shell to a lower shell to fill that in. And these are typically either perturbed energy levels. You might get slightly different energies because of the way the electrons are filling the shells. And so typically the lines are called satellites to the lines from ions in the ground state. And so you can get a sort of several varieties of these, which are kind of interesting, and tell you something about the state of the medium. You can also have some of the semi-forbidden transitions. You can also have energies where the spin changes, or sorry, transitions where the spin changes. So you have a transition between an energy level, which has a different multiplicity and a different value of the total spin number. So you can get a transition from, say the 3p1 or 0, 1, or 2 state to the 3, 0s state, or likewise the 1p state to the 1s0 state. So this is an example of helium, which is the most common form of this. And part of this you actually will see, so you have different different sort of populations of the different lines. So you get, for instance, you can have a transition here, then here. You can have one that goes straight here. You can have one that goes here. And then you can have this one, and this one will actually emit 2 photons to get down to this state. And so you have different sort of ways of populating this, and there are different ratios between these different values, and those ratios depend pretty intimately on the internal physics. So if you measure the ratio of these different transitions, the R versus the I versus the F line, for instance, it's a very sensitive probe of the temperature and the density of the medium. Similarly, so this is for helium, you can have helium-like ions. And so this is the helium-like ion of sulfur. And so this just shows, again, a similar set of transitions. So you have the 1p1 to the 1s0, and then you have a 2 photon transition here. So you can have a 1 photon transition up, but a 2 photon transition down. This is generally not very likely, the 2 photon emission. So the probability is very low. Then you also have these sort of hyperfine structure states, and you then have transitions which go back and forth between the ground state and these various states. And then you have this sort of lower level here. And so you can have various transitions between all of these. And so in the X-rays, this is now 4 angstroms. So this is very high energy, sort of, think about 3 keV or so. You'll see the W line here, which is this transition, with the X and Y, which are here, which is a blend because these are very, very subtly different. And then you have the Z transition here, and that's here. And so the ratios of these, again, will tell you about they're very sensitive to the temperature and the density of the material. And so they're unique probes of that material. And these are typically known as intercombination lines, this particular set. So with all of that, see, those are the various nomenclature for the different lines. and we want to actually know how we populate the different levels. And so you should have probably seen this in previous quantum mechanics or statistical mechanics. But we want to, understand how the lines are populated or how the levels are populated. And then that will tell us something about what the probability of a transition one way or the other is. And of course, the details of how you populate these levels is kind of very intricately tied into the various thermodynamic relations with the various ions. And so this is very tricky. It's a very detailed process of understanding how a level becomes populated or depopulated. If you assume thermodynamic equilibrium, then things become a little bit simpler. And so if you know that everything's determined by a single temperature, it becomes a little bit easier. And so if you have an ensemble of atoms, then basically the number or the relative number of atoms at a given level is proportional to G times the exponential of that energy transition divided by the temperature of the system. And here G is the statistical weight describing level degeneracies. And so if we have some energy I, which is the ith level in an atom with respect to the ground state, then the number density of atoms in that particular level is given by Ni. And so the total number of atoms is just going to be the sum of the number in each state, right? And that'll give you the total number density. And so the number in the ith state is related to the total number density divided by U, which is the partition function, which is the sum of all the different statistical weights times each sort of exponential here, and then times the particular statistical weight for that particular level. And so this thing is a function of temperature, right? So this exponential goes 1 over kT. And so typically if you have a very, very high temperature, right, this thing will be lower and lower and lower. But if you have a low temperature, this thing is relatively high. And so generally only the ground state for low temperatures becomes important. And thus this partition function just reduces to the ground state statistical weight. If we have a finite temperature, the sum will, the sum diverges here, and we have to consider how we cut off the sum. And typically we can note that the gas typically will have the distance between particles is going to be finite, and so the outer electrons become unbound. And so at some point you can stop summing because you figure that those things will be stripped off. And so this would reduce the ionization potential slightly in this case. We can estimate what the characteristic cutoff is. And so if we adopt a sort of Bohr model of the orbit corresponding to some maximum n level, for that particular n level, we can think about the interatomic spacing. And the interatomic spacing is going to go roughly so n squared max times a here, divided by z is roughly going to be the cube root of the density, or 1 over the cube root of the density. And so this is just the surface area is growing and to the point where it becomes comparable to the density. So once these levels start touching, you have a problem. And so based on that, you can calculate n max, which is proportional to the atomic number, and then the density with a very small power. And so if you take something like hydrogen at a density of 10 to the 12, then n max is going to be about 100. This is a huge density, right? So typically you could integrate all the way out to 100 and you still would be fairly safe. This is a simple model, the Bohr model, so it doesn't take into account the Debye screening that we talked about before and other minor effects, which you'd have to actually throw in to figure out the actual calculation of where you should cut this off. In general, it's not very well understood how it works out there. And as there have been many PhD theses on this subject. And so there are very small, fine details about exactly where you cut it off. For most things that you will ever encounter, you probably won't need to care about this. So in general, this when we talk about astrophysical cases, this cutoff is not critical. And if we think about temperatures up to 10 to the 4, our partition function is more or less still going to be equal to G naught. So most things, even at 10 to the 4, most things are going to be in the ground state. And of course, at 10 to the 4, this is going to be pretty decent for a fraction of the solar interior, the ISM, accretion disks of AGN, and so forth, right? So in most astrophysical cases, we're not dealing with temperatures beyond this. And so we really don't have to deal with more than a few levels of the atom. Okay, so this is, of course, assuming that the distribution of levels results from a density of single atomic type in thermodynamic equilibrium. And of course, the universe is not that simple. And so obviously we would want to investigate distributions with various stages of ionization of a single atomic type or multiple atomic types. And so we have to investigate that using something called the Saha equation, which we'll come to in a second. Are there any questions on this, anything I've touched on so far?
Yes. If we detect someday a magnetic monopole, how could the lines change? Transition lines.
Well, I guess we've put constraints on it already to some extent. So I don't know that it would change much about what we know. But if we did detect it someday, we would have to factor it in where it was relevant. But we already have constraints on it at the moment, right? In that we get by without it in many cases, so it doesn't seem to be important in most physical situations. But there may be a physical situation where it becomes relevant. But again, beyond that, I don't really have an answer for you. Other questions?
I have another question. Can you hear me? Okay. So in general, the term, the word, specific word forbidden is only for spontaneous emission. I mean, the idea is that forbidden lines are possible to obtain due to collisions or another processes. In terms of ideas, forbidden and semi-forbidden lines are useful to trying to study other properties related to the collisions. I mean, the density or temperature of the medium.
Yeah. So we'll go through a couple. I think next lecture we'll go through some of the empirical sort of calibrations that you can use to get at that. And I think later in this lecture we'll talk a little bit about that. I can't remember if it's this lecture or next lecture now. They blend together, but yeah, we'll talk a little bit more about how to extract physics from collision ionization or photoionization. But the point is that those transitions typically will de-excite in other ways unless they're populated, unless you get a level inversion that allows them to sit there for a while and you have enough of them, then you will see the transition. But if left to their own devices alone, isolated, you wouldn't see them. They would take a long time. That's kind of the, and so there would be other ways of losing the energy that the atom had, if that makes sense.
Yes, yes, thank you.
Any other questions? No. Okay, so we'll head on to the Saha equation. So we can think about a simplified version of the Saha equation where we only have two states. And so we have a neutral atom and we have the first stage of ionization. And so then we can consider the Boltzmann law for this. And so we have the upper state. This is basically the differential number of ions in the ground state with free electrons in some velocity range. And so this ratio to the ground state is proportional to our statistical weights and our exponential of the ionization potential and some velocity here with respect to the system. So this thing is the ionization potential of that particular level. And then this thing is, as I said, the number of atoms in the ground state, and this is the statistical weight. Here, G here is equal to the statistical weight of the ground state and the statistical weight of free electrons and the ground state ion. All right, so this is both of those things. And so the statistical weight of the electron is simply given by this thing here, which is the phase space and the momentum space. Right, so this is just the uncertainty principle. The extra 2 here denotes the fact that it could be spin up or down and occupy the same space. Right. And so we can note that this thing here, the number of electrons times the space quantity, this will equal 1 for a volume which contains 1 electron. And then we can define the momentum space, right? So these 3 momentum vectors as just the mass cubed times velocity squared dv. And so we have a small velocity range. So it's somewhere in there is what the momentum space would be. And so then plugging that in here, or plugging it in for the statistical weights, we can say that for non-relativistic electrons, we end up having that this ratio here goes as this thing, which is the statistical weight of the first stage of ionization. This is the ground state, this is the number of electrons, and this is the ionization potential and the electron motions. And so depending on the, right, so we have ground state and we have the other state will be the first state where you have 1 electron stripped off. So you have some ions and you have some electrons. And so it's counting all of those things in here. And so it depends how the number or how the equilibrium between those exists is dependent on the temperature, is dependent on the electron velocities, it's dependent on the ionization potential and then the number of electrons, basically. And then these statistical weights. So we can think about the total number of ions by integrating over the velocity space. And so we have, this is the number of ions, the number of electrons, and the total number of ground state, this ratio here. So all we've really done is, right, we're integrating this thing and we move this NE over to the other side. So that's going to be equal to the things that are not proportional to the velocity. And then we have, something here where we've now kind of pushed X as a variable that is substituting for the velocity and has this normalization here, which is related to the temperature. So we're taking the integral of this thing here. And this integral turns out to have a fairly convenient solution. So we can just plug in pi over 4 here. And so we now have the ratio of the levels is dependent on the temperature to the 3 halves and some constants, the statistical weights, and the ionization potential relative to the temperature. And so we can, for a given state that's in equilibrium, we can calculate what the ratio of these two levels are. If we wanted to know the number of ions or atoms in any given state, we could then use this. And so this is the ground state over the total, and that's equal to the statistical weight divided by the partition function. We also could look at the first ionized state versus some other ionized state, and that would be this statistical weight divided by the total partition function here. And so we can calculate any state and with the number of electrons to the total number as being the partition function of that particular state divided by the total partition function times the temperature times the ionization potential, with this extra factor of 2 in here. So this allows you to kind of understand in a basic level how you would populate the different ionization states for any system which is in thermodynamic equilibrium. So this is known as the Saha equation. And so a similar relationship would hold with successive ionization stages. And so you could generally say, okay, we want to know what the ratio between the J+1 state is and the J state, and that would be simply this. You can rewrite all of this not in terms of the numbers, but in terms of the pressures, assuming an ideal gas law. And so then you could rewrite this as the pressure in this state versus the pressure in this state, and the pressure of electrons is again related to the partition functions. And now you have a sort of simpler, well, you have the constants here, you have a temperature which now goes not as 3 halves, but since you have an extra KT here, right, you've multiplied both sides by that, you now have KT to the 5 halves, and then this exponential. And this would allow you to understand how gases, how the different states, ionization states of the gas are in pressure equilibrium. When you have a different, well, basically a mixture of different species here, then you typically want to take, you want to relate this, this equation relates the pressure to the conservation of nuclei. And so you want to have the sum of the nuclei of all of these different stages is, of course, equal to the total number, which should make sense. And so the number of electrons, right, will also, if originally you had parity between the charge parity or conservation of charge, then the total number of electrons should then be equal to this. So the sum over all of the atomic numbers and all of the ionization states. And so ultimately the total NE and the total N should balance out to roughly neutral charge. So this is fine for simple problems, and typically for anything that gets even a little bit complex, you have to do it numerically and often iteratively to find a solution. If you can isolate the bulk of the population to a few ionization states, and again, we had said, in the previous slides, I just mentioned that, okay, for most temperatures, the hydrogen will mostly be in the ground state, right? And so the ground state, the first excited state, the second excited state, that would be all you would really need. And that, of course, reduces the complexity here a lot. For hydrogen, this can be worked out analytically. However, if we move to helium, we already have to make a lot of approximations and kind of not get everything exactly right. If we go even higher, then we have major problems. Sorry, I have a fire apparently. Okay. think it's sort of going away. It's not in my building. Maybe. Okay, so for instance, this is you can do this, but you need sort of programs to do this. And if you think about other higher level elements, there are certain elements such as alkali metals where they have very low ionization potentials, and so they can make very big differences to the equilibrium state, even though they're relatively rare in abundance. And so these can actually strongly affect the electron number density, which is then, of course, coming back to, right, comes back to this. And so if you increase the electron number density, that changes this, right? It changes this ratio. And so alkali metals like sodium, potassium, rubidium, cesium, typically the leftmost column of the periodic table are the ones that are strongly affecting the number density. So, okay. So we can take an example here. So we have the Boltzmann equation for two different level populations. And let's say we have hydrogen. And so neutral hydrogen has a statistical weight. The statistical weight goes as 2n squared. So if n is 1, this is 2. If n is 2, this is 8, etc. And so we want to know at what temperature do we have, or at what temperature are the number of atoms in the first excited state roughly 1% of the number of the ground state atoms? Right, so we just want to know, okay, what temperature do we need to populate the n equals 2 level at 1%? And so, typically, if we look at the energy required to go from n equals 1 to n equals 2, this is about, well, it's 13.6 minus 3.4, so it's roughly 10.2 EV. And 1 EV is equal to this. So we also have the Boltzmann constant here. And so if we want to calculate n equals 2 here, equals 1% of n equals 1, then this ratio, right, has to be 0.1. And so if we have 0.1 here, we can plug in and we know what this is 10 EV. And so we can factor in what this exponential is. We have the statistical weights, which are as 8 to 1. And so if we plug that in, we require a temperature of about 20,000 Kelvin, which of course justifies our previous sort of assumption that we need, for most things of 10 to the 4, we're going to be in the ground state, right? Most of the population is going to be in the ground state. We could do the same thing for 10%. And so 10%, we just plug this in, and you can do the math in your head, of course, and we get about 32,000, right? And so on and so on. And so, of course, there are very few stars which have this surface temperature. Obviously, interior to that, maybe we have to deal with a few states, but you're never going to populate many states until you get to very high temperatures or very interior to the star. Okay, so that's one example of a very simple example of the Boltzmann equation. We could do something similar for the Saha equation, but remember the Saha equation is describing ionization states, not level states. And so we could think about the going from the number of some sort of ionization state, ground state, to an ionization state and the number of electrons. And this is going to be equal to our partition functions and our sort of temperature portion and our exponential. And if we plug in that we have a pressure here, we can gauge that this ratio here will be equal to the temperature, the statistical weights, the pressure of the electrons, the temperature, and this, right? So we throw the electron back over here again. So if we think about the stellar atmospheres, and we understand that the pressure here is going to typically be in the range of about 1 to 1,000 dyne per centimeter squared. And so we can estimate what's the fraction of atoms that will be ionized in an atmosphere that has a temperature of 8,000. And so we can look at the second version of the Saha equation here, plug in our pressure term, plug in our various our ionization potential, and what we want to know is the temperature here, right? So we're plugging in our temperature. We want to know what the fraction is here. Okay, so we do that. We plug in our various constants here. The mass of this particular the MR here is going to be roughly equal to ME. The ionization potential of hydrogen is about 13.6, and we'll choose a pressure of 209, sort of in the middle of this. And so if we do that, we need to figure out the statistical weights. And so for the statistical weights, what we're really trying to ask here is how many different states J are there with the same energy EJ. And this is sort of, what we're doing here is comparing the only possible ionization states of hydrogen, so neutral and singly ionized hydrogen. And so the neutral hydrogen has an ionization state or a statistical weight which goes like this. And so we can note here that we're using the Boltzmann equation to provide input to the Saha equation. And then we can use, so we can assume that our statistical weights are sort of order this. And so at 8,000, we have a ratio here. If we plug in our various values for this, we have something which is of the order of this very small number. If we calculate it at 12,000, it's of this order. And so this is NH2, actually what we want is the number of ionized atoms. And this is the number of neutral to ionized. So we want the total here. So we actually want NH plus H2. And so that is equivalent to this. So this is fractionally more or less the same since this is a very small number. So this is more or less 1, and we just get away with this. So at 8,000, we have that roughly 1.5 times 10⁻⁶ hydrogen atoms are ionized for every hydrogen atom, or for the total number of hydrogen that's there. So in essence, 1 out of 1,000,000 atoms are ionized, right? At 12,000, we have something like 2 out of 10,000 are ionized. So it's a very small number are ionized. And then, of course, if you go back to the Boltzmann equation for these sort of temperatures, you have something like less than a few percent are even in the N equals 2 state, which kind of makes sense. This is just probing the tail end of the distribution, this thermal distribution. Okay, so you could do this for a variety of different systems, but the hydrogen one is really the only one where it's sort of simple to calculate out. And for other ones, you need to actually start to do energy balance between, well, if you have a pure helium, for instance, you could kind of deal with that, but then if you have hydrogen plus helium, then you have to actually deal with the balance between those two atoms. And then if you add other trace elements in there, you need to deal with those as well. So typically, this sort of thing is done with codes like Cloudy or what's the other one? There's 3 or 4 different codes that will allow you to sort of do this for still, I would say, somewhat simple systems, or you have to make lots of assumptions, but you can do this and build up a sort of coherent ionization balance. Okay, are any other questions about Saha equation? I'm not going through this in too much detail because I just mostly want you to, I think you should have seen it before. And it's mostly just to remember where it, what it is, how it sort of incorporates into greater astrophysics. Okay. So with that, then we'll come back to the line width, which is an important factor here. And so here we want to go back to our, if you recall the scenario we talked about where we have an oscillator, we think about the atom as an oscillator, and we want to know what the spectrum that is emitted will be like. And we set up this radiation, radiating oscillator, and we had to take into account the radiation reaction in this sort of situation. So we had a dipole approximation, and we had the emission, right, via the Larmor formula went like this. And this corresponded to a radiation reaction force, which had a triple derivative here of R with respect to time here, right? And so the radiation reaction force would tend to dampen this oscillator. And so if we look at this force, so if we take this force and we take basically the average value of the force times the velocity here, we end up getting this thing, which has two terms here. And so we have the cross product of the velocity and the acceleration, and then we have the sort of input value here of the original dipole approximation. And so it's the total radiation that would be coming out when you involve dampening would be this value here, right? So it would be the average of this quantity. This thing typically in the average will equal 0 because the velocity and acceleration should be out of phase for a harmonic oscillator. And so we can derive an equation of motion for the oscillator, which looks like this. And therefore we have this dampening force. So if this dampening is weak, then we still have roughly harmonic motion. And we can think about this triple derivative is approximately equal to this harmonic oscillation. And so we have something which looks like this, where this gamma is now taking on all of the constants in here for the most part. And this is known as the damping constant, the classical damping constant. And this should be much less than the frequency of this expected transition. Right, so the frequency of the oscillation, which is giving you more or less what the frequency of the line will be, that frequency, this dampening should be much less than that, which is why we would say it was weak dampening. Okay, so in this sort of scheme, we can think about what's going to happen with the line that's coming out. And so an approximate solution of this is then going to be R goes as T here, where T is has some constant of proportionality, and then you have some exponential which goes as the dampening times the time, and then you have the actual oscillation with respect to its frequency. And so here we also can think of the electric field of the oscillator, and so the electric field as a function of time is going to go as this, right? So it's also going to have this dampening, also have this frequency time dependence. And so for time greater than 0, it will be this. For time less than 0, it will be 0. And so we can take a Fourier transform of this thing. And so we have that the frequency, the field as a function of frequency will go like this. So it goes as the overall electric field amplitude, but then you have some component here, which is imaginary, and then you have the damping constant. And the intensity should go as the E field squared, right? And so the intensity as a function of frequency will be that. And so of course, when we square this, we get rid of the complex number. We also can think about the frequency as being, the oscillator frequency is just 2 pi times the actual frequency. And so we then have an intensity as a function of frequency, which goes as some normalization times some value here. This is now sort of proportional to the damping constant, but divided by 2 pi. And so we can plug in our values here. Oops, coming back here, we can plug in our values for this, but now in terms of the transition frequency here. And then we also have, so that's this extra normalization. And then we have our frequency dependence, which looks like this. And so as this frequency approaches V naught, this will become 0, right? And you have some value here. As this goes away from this, this will become larger and this will go down. And so you have a peak around this frequency V naught, and then some transition away from that. So if we look at it here, and this is normalized, so this is the frequency with respect to frequency naught divided by our sort of constant here. This will go out as sort of -2, -4, 2, 4, and then we have some peak, which is related to the amplitude. And so the profile will look like this. So it peaks at the center and goes down like this. And this thing here, it turns out is the full width half maximum. So our capital gamma is the full width half maximum for this line, and also known as the natural line width. And so the important thing to note here is that this profile is not Gaussian. This is what's known as a Lorentz profile, right? And so it takes this particular form. So an oscillator, right, if we think about the change in n level from one level to another as approximated by this oscillator, then we should have a emission line which should have this sort of properties. And this width here is dictated by just fundamental constants and the frequency. Right, so that's what's known as, that's why it's called the natural line width. And this is the natural line profile. So it should be a Lorentzian if nothing else is influencing it. Okay, questions? Okay, so of course, some things will influence it, right? And so that's what we'll get to next. So the first thing that influences it is, of course, that every atom is not by itself, but it's existing in some phase space with other atoms, and the atoms have motion, right? And so we might see one single photon from one atom, which is traveling in one direction, and another photon from an atom, which is traveling in another direction. And so those atoms will impart a Doppler shift on those respective photons. And so what that means is that if we have a distribution, which is a distribution of, say, ions with a radial velocity Vr, and it's in equilibrium, we will have a Maxwell-Boltzmann distribution of velocities. So the number at a given velocity is going to go as this functional form, right? So the number of total atoms related to the square root of its temperature, and then some exponential for the tail of the distribution. And so the Doppler shift is just the shift in the frequency as a function of Vr, right, divided by C. And so the strength of the emission is then going to be given by this exponential here, which is related to the difference in frequency with respect to our rest frequency of the line transition. So that's just the sort of width of it. But you have an extra factor here, which is related to the temperature. And so the temperature, if you have higher temperatures, you're going to have a lower amplitude here, right? If you have lower temperatures, you have a higher amplitude. And what that's saying is that the width of the profile, you know, if you broaden it, you're going to have a lower amplitude over a larger frequency range. And so if the natural line width is negligible compared to the Doppler broadening, then obviously the Doppler broadening dominates. And so then the line width, which we can show as this functioning form here, is going to go as this sort of exponential around this line center divided by some sort of normalization here, which is related to the temperature and the original velocity line center. And then it's normalized by 1 over delta V squared and square root of pi. So this is Gaussian, right? And so if Doppler broadening is dominant, then you will have something which has a Gaussian profile. We can think about these things in terms of going back to the Einstein coefficients now, and thinking about the, you know, if we have the absorption cross sections, they're going to be related to the statistical sort of properties, the number of ions, the number of atoms, and so forth, the number of photons, and then they have a functional form which depends on the line profile. And so now our absorption cross-section, or absorption coefficient, is dependent on the line profile, right? Which is now dependent on perhaps the temperature of the system or the natural line width of the system, and so forth. So we can, you know, think about this absorption coefficient in this relation. This is going to have a frequency dependence, and we can think about this as the number of atoms and then some cross-section, which has a frequency dependence, right? And so this frequency, this cross-section, if we were to rewrite all of this, this cross-section is now going to take on this profile. And so at least in the classical limit, we can think about the absorption cross-section for electron scattering. And this is based on the radiation-driven harmonic bound particle. And so we calculated this before, right? This cross-section as a function of frequency goes as our Thomson cross-section, our tau, which is of course related to the number of particles along the line of sight, and then we have some factors here. And here again, actually this gamma is now slightly different because this is just our harmonic bound particle. So this is the time for the radiation to cross a classic electron radius, but it goes sort of as this functional form. And so this, we can see this functional form is fairly similar to this functional form, right? So here we had our gamma squared, we have a gamma here, and we have our frequency dependence, right? And so here we have frequency dependence, gamma squared, and gamma. And so we've more or less just sort of rewritten it a little bit, but this thing ends up being the full width of the line profile. And so plugging in so integrating this cross-section over all frequencies, we will end up with this. And so if we do this in frequency space, we'll end up with this. And then this thing should equal this, which is our Einstein coefficient and our frequency of transition from lower to upper. And so we can derive our lower to upper Einstein coefficient as being related to this. Okay. And we can make a quantum correction. So that was, of course, the classical oscillator strength. If we make a quantum correction, we can do this simply with a fudge factor. And so then we have this sort of relation. Now we have this extra fudge factor here. And typically this absorption oscillator strength is of the order of 1. So the classical approximation is decent, but maybe you have, for some transitions, you have to multiply by 5% or 10%, something like that. So if we think about the cross-section again of this particular transition, right, we want to note that the line center cross-section for an atom corrected for Doppler broadening then would look like this. So the cross-section looks like this, and then we plug in the profile here for our Doppler formalism. And so we have this 1 over delta VD. And so this thing, if we now plug in our oscillator strength here, then this thing will look like this. And so we have our quantum correction, and we have a couple of constants, our Bohr radius, and then 1 over the Doppler velocity, the Doppler frequency shift. So this cross-section for a given frequency is reduced by the large temperatures, right? So what I was saying before, if you have a large temperature, the Doppler broadening broadens the overall line, so it spreads over larger frequencies, right? And that's contained in this thing here. This goes as the square root of temperature, right? So here. Okay, so that's a little bit of insight into the cross sections. And so if we think about having turbulent broadening, in addition to Doppler broadening, so turbulence could be from something else. You could have magnetic turbulence, you could have microturbulence, whatever. So this would be, turbulence that's small in comparison to the mean free path, microturbulence. And these motions would be accounted for by an effective Doppler width. And so this delta nu d would have the classical Doppler component, but then you have an extra factor here, which is a turbulence. And so you could plug in some sort of turbulent component here, and this would just give a modified Doppler component. And so if the turbulence is on larger scales than the mean free path, it's hydrodynamic or magnetohydrodynamic. If it's on something smaller than the mean free path, then it's this microturbulence. And so here, basically, we would want to take whatever profile one has, and this would include collisional effects, et cetera, which we'll describe later, and integrate over the hydrodynamic turbulent distribution to see what the underlying, once you remove the hydrodynamic turbulent component, what extra shapes you have, which might modify things. Okay. So the natural broadening, as I mentioned, so you have atomic levels here, and basically the natural broadening comes to some extent from the uncertainty relation. And so you have some delta E and some delta T, and this combination, right, gives rise to the Planck constant divided by 2 pi. And so if you have a spontaneous decay from an end state, then this component is going to be the sum of all of our spontaneous emission components, summing over all of the different states. And so if you have an energy in the nth level, that state is going to decay like this. And the emitted spectrum here will be determined by a decaying sinusoidal form of the E field. And so, or we could also think about if the radiation is harmonically bound with undriven particles. So this particular sort of uncertainty translates into this Lorentz profile, which looks like this. So this sort of classical derivation, again, has a place in quantum mechanics through the uncertainty principle. So again, as you can apply this particular profile into the Einstein equations to understand what probability, for instance, of you might have a photon which is not exactly at the line width, at the line center, but it's offset. And so there's some probability that that photon will be absorbed and be able to liberate the electron to a higher state, right? Even if it doesn't have quite the right energy, or if it has a little bit too much energy. So, typically, if you have both the upper and lower states are broadened, then this total broadening is kind of given by the sum of these broadenings. And so this determines the total width of the emission line that comes out, right? Because you're going to have some interplay between the different, going up and going down. Okay. The other thing we can talk about is collisional broadening. And so the collisional broadening happens, basically you have, if the emission of radiation suffers collisions, you have a phase of the emission ends up being lost. And you can see here, like, the collisions will induce a time-dependent random phase in the electric field that ends up occurring here. And you can estimate the power that's emitted here as a function of frequency by doing a Fourier transform of this energy-dependent E field. And here we assume a Poisson distribution for the number of collisions with some mean, so some Poisson distribution about the mean. And then we showed here, basically this collisional effect will end up giving a Lorentz profile. So if we have our electric field, and so this electric field, it had the natural broadening, or this dampening term here. It has the oscillation here, and we add an extra component here. Right? And this extra component is the randomization, the phase randomization. So A here is our total proportionality constant. This is the spontaneous decay rate, also the width. And so then we have our internal frequency, omega naught. If we take the averaged power spectrum, that's the taking the average of this. So we Fourier transform this, and we take the average and square it. This is going to be equal to this. And so if we plug in what that is, right? So we have this whole thing here is this, right? So we're taking time one, time two, we're taking the integrals between those two things. And so we have our component here of our oscillating wave, which is going to change by this amount. We have our spontaneous decay, which is going to change by this amount. And then we have our randomization, which will take place here. And so we can think about the fact that the phase here is going to be randomized. And so this thing will be equal to, we can separate out this component into this thing, and we can take the average of this. And so this here will be a delta phase change. And so we can think about, this is going to be the change of phase in some time interval, which is given by this time interval. And then this randomness of a collision happening or not. Basically this is telling you the probability with which you'll have a collision of one or more in this interval. And so this average is going to vanish as you have a sort of rapidly oscillating function, right? So this is just resetting everything, but in the average, it will vanish. If no collisions occur, then the quantity ends up being 1. And so because it ends up vanishing the average, we can take it out. And so we end up with the same integral that we had effectively before. And so we end up with a Lorentz profile, but a modified version of that. And so if we adopt a mean rate of collisions, which is given by this value here, unfortunately, this is also frequency, then we can estimate what the Poisson distribution of collisions is going to be. And so we have a Poisson distribution here. This is the probability that no collisions will occur in this time frame. And so the Poisson distribution will take this form. And so this is ultimately going to be equal to this time change times this mean rate of collisions. And so this thing here, this lambda is this collision rate times the delta time, right? So it's just the probability of collisions in some time. And then X here is the number of collisions we're seeking. And so in this case, we're seeking 0. So this component here, right, in the average is going to be equal to this thing. So it's just the time average of this delta t times the number of collisions we expect. And so we can plug that in, we have this thing. And so what this ends up doing when we take the integral is we have a modified width due to the collisions. And so, you know, this is just an extra additive component on our gamma. So we also had, you know, let's see, where was it? So this was just gamma times t. And so ultimately we can just take this to be v collision times t, right, delta t. And so we group them all together. And so our modified capital gamma is just the regular gamma times 2 times the collision rate. And so depending on the properties of the density of the material, the temperature of the material, you'll get a collision rate. And so that will come in and broaden it, but broaden it in the same sense of having a Lorentz profile. Any questions? No. If you think of anything, you can ask them in a second. So we can now think about a more complex situation where we have both Doppler broadening and Lorentz profiles, and one doesn't dominate. And so the combination of these two things, if we were to write out this sort of profile like this, we have this combination here. We already had this modified width here, and so now we have, taking into account all of these different factors, we have the Lorentz. Basically, this is the average of the Lorentz profile weighted by the velocity states, and so you have the Lorentz profile, the sort of delta nu here. You have this extra component, which is our Doppler component. You have a modified Lorentz profile here, and then this thing is taking all of the velocity states of this particular component. So here, this thing is a line of sight velocity only, and so we can simplify this ugly thing into something called the Vought profile. And so the Vought profile has a functional form which looks like this. So the Vought profile has this functional form, and so we can think about this profile here as being 1 over the Doppler velocity, and again the normalization of 1 over square root pi, and then this. And so this thing, so A here is now this, and we also have this exponential, which goes as this, and then we have u minus y, where u minus y is this thing. And so A is here, u is this profile divided by the Doppler velocity, the delta Doppler velocity. And so if A is small, then what happens is the central line is dominated by the Doppler profile, and then the regions away from this line center, basically the wings, are dominated by the Lorentz profile. And it's probably easier to see. So here is the Lorentz profile, which is sharply peaked and has then these long wings. And here's the Doppler. So the Doppler profile is here. And so the Vought profile is this combination. Yeah, right. So you have something which is lower and ends up having sort of broader wings and then extends out. And these wings are much broader than the Gaussian version of that. And so typically you could ask a very intelligent or naive question, which is, what line profile should I fit? And that will depend on the physics, right? It depends on the physics, because I mean, ultimately you could fit a Vought profile, and then the parameters of the Vought profile, if you have enough signal to noise, right, you could decouple all of them, and you could figure out what is the Doppler component, what is the natural width component, and so forth. Now, that intimately depends on being able to measure the wings. And so if you do not have high signal noise data, you can't tell, right? Because you're going out. And so say you have continuum here, right? You're trying to fit this thing on top of continuum with some noise there. And so it's very difficult to see this, but maybe you can see this, right? And so maybe if you have enough signal noise at 2 times the width of the line, then you might be able to say, oh, I have a Lorentz dominated profile or a Vought profile or a Doppler dominated profile. And so to some extent you can guess based on the physics, like what physical objects you're looking at. You can say, well, I think, given what I know about this thing, I'm probably going to be seeing the Doppler component, or I'm probably going to be seeing the Lorentz profile. But it's a non-trivial question. So typically people will do Gaussian profiles just because it's easier, but you can underestimate the total amount of, right, if you integrate this, and so if you estimate the Lorentz profile with a Gaussian, right, you only are estimating this, and so you get the total line strength off by a decent amount because there's a lot of power in the wings. Okay. So that's all I really wanted to say, and we're well out of time. Any questions? Hopefully you learned something. But this mostly explains all of the different line possibilities that you'll see, line profiles that you'll see. Then you will have complications, because if there's actual velocity structure, right, then you'll have that velocity structure imprinted on the line, and you can do physics. You can measure if you see a disk, you can then measure the motions of the disk via the Doppler motions, which will look like that. Or if you see a shell, right, that will have a certain profile. A shell will have a square profile, for instance, right? And a sphere will have a centrally peak profile, and so forth. Okay. Any last questions, thoughts, doubts? Everything was clear? Okay. All right. Well, if you think of questions, you can email me. You can ask them Wednesday's class, etc. Okay. Okay. So yeah, on Wednesday's class we'll talk a little bit more about some of the physical applications of this. In addition to, we're going to go into bound-free, free-free, bound transitions as well. Okay. All right. See you guys.
Bye.
Bye bye.